Welcome to this live stream. I'm delighted to be again with Professor Scott Turner. How are you doing, Scott?
I'm doing great, Subwer. Thanks for hosting me today.
It's lovely to have you back. Last time I actually was going live in my house, and at times we lost connection. So I'm so happy to be back in the studio and
Yes.
prepared with my questions as well, as opposed to just having a free-for-all discussion. So
Yes.
we're going to be discussing your idea of the extended organism, which obviously is a play on the extended phenotype, right?
Yes.
So there's that. So before we get into the actual argument and the sort of the ideas that you've put forward, the question I want to put to you is, what prompted you, or what inspired you to work on this book?
On the extended organism.
Yeah.
Yeah. I had been working for a couple of years on these termite mounds, and I came into it with the idea of exploring a longstanding story about how these things worked, and it's centered around the name of air-conditioned termite nests, if anyone wants to look up some of these papers. And one of the things that I discovered fairly quickly is that they had that totally wrong. I spent a lot of time trying to elaborate on the air-conditioned termite nest, and many of the assumptions that underlaid that idea, I was testing experimentally. I was working to try to verify it, and I couldn't verify any of it. Delving deeper into questions of, well, what are the assumptions behind this air-conditioned termite nest idea? Every single thing I tested seemed to be wrong. Well, it seemed to disagree with the assumptions behind the air-conditioned termite nest. And naturally, whenever you're confronted with something that you had accepted for a long time, I'm a physiologist, I'm interested in how things work, and here's a classic story, and it was all wrong. Naturally, you start to think, this is one of the beautiful things about science. You test an idea, you discover that it's not quite what you expected, and that starts you thinking about why it's not right. And the more I thought about it, the more it became clear that there was a very interesting story there, and the very interesting story was turning on just what the nature of the organism was. If you look at nature through a particular lens, namely that animals and actually plants, indeed, they build environments. The termite mound is a quite stark example of that. It's a built environment, and there are lots of examples of that out there. So I got interested in the idea that, well, these things have function, they have physiology, and so that was the genesis of the book, The Extended Organism. And of course, the subtitle of that is The Physiology of Animal-Built Structures. And this tied into another interesting tradition about animal architecture. Carl von Frisch wrote a very famous book about this. Again, I thought interesting ideas in there, but I didn't think that the trope actually went far enough. It didn't really see the radical implications of why animals built structures. And that was, of course, my departure from the extended phenotype. I was actually inspired by this. I really admired the extended phenotype. I thought it was one of Richard Dawkins' most original works. But I, being a physiologist, I've always been kind of uncomfortable with this notion that genes are the masters, that the organism itself, the very complex functioning organism, is just kind of a vehicle for it. And I had been thinking for a while that, well, maybe there's not much of a distinction between phenotype and genotype. And of course, this distinction has been central to gene selectionism the gene selectionist form of Darwinism for a long time, and the distinction seemed kind of arbitrary to me. It seemed to be conceived because there was a need for it to be able to prop up the neo-Darwinian idea of gene selection rather than it having some kind of an objective reality. Genotype is very distinct from phenotype. I wasn't buying that, and so the title of the book was inspired by the extended phenotype, but I wanted to draw the distinction that really what we're talking about here is extended organisms, that ways in which living things manipulate environments, build them in order to basically make them part of the phenotype, but actually make them part of the organism as well.
Yeah, I mean, the way I would put it, I mean, I like the way that you introduced the topic, but with Dawkins' idea of the extended phenotype, it's almost like the extended phenotype is the maximum extension that you could get from a gene-centric point of view. And what you show quite clearly in your book is, drawing the boundary of the organism's, what we define as an organism at the skin, right, is just arbitrary. So I think your idea is, quite novel, and I think the extended phenotype got a lot of traction. And actually, this book is the real paradigm shift for me, because it's really challenging some, base assumptions about what is selected. So to take the conversation a little bit back in terms of classic Darwinism and the modern renditions of it, I think it'd be helpful if for the viewers you explain what was classic Darwinism and how is it distinct from the modern renditions of it, and in particular how classic Darwinism had a focus on having a theory of adaptation, design, cognition, consciousness, and modern renditions are always gene-centric and just focused on what is inherited.
Yeah. The classic Darwinism is basically what Darwin himself thought, and that's how I define classic Darwinism. And of course, everyone knows what a superb naturalist Darwin was, and the depth of the questions that he was struggling with, and his idea of natural selection. It was solidly based in the organism. The first chapter of The Origin of Species was about pigeons and breeding, and we all know the story there. And he had a very, very keen eye for the organism, which was what's the species, kind of how the species was defined back then. And he struggled, I think, for most of his career trying to distinguish his way of thinking from the thinking of his French predecessors, like Lamarck and Georges Cuvier and various other people. And the point of struggle there was how to explain heritable adaptation. The whole concept of fitness that existed back then was turned. It turned fundamentally on the concept of adaptation. In the struggle for existence. The more apt function, that is, the better adapted, the more likely an organism would be to successfully live and also successfully reproduce. And of course, there was a lot of ancillary inputs in that. Spencer, for example, he introduced a lot of terms that we normally associate with Charles Darwin, but nevertheless, it was all consistent with this Darwinian idea that adaptation is basically what we mean when we're talking about fitness. Excuse me. And the struggle with trying to explain evolution and reconcile it with Lamarck's ideas about heritable adaptation. Of course, this was the origin of Darwin's theory of pangenesis, and it didn't really go very well because it was kind of inconsistent with emerging trends in biology. Weismann was trying to work out the locus of heredity. Of course, he eventually localized that on the chromosome, and various other developmental biologists, for example. And this uncertain territory about just what heredity was, how it fit into adaptation, and things like this. This was what ultimately led to the fall of Darwin's pangenesis idea, and he ended up describing it as his bad dream. He dreamed that there had to be a reconciliation, but couldn't quite do it. And so, being the rational fellow that he was, he sort of said, "Oh, this was about a badness, and I couldn't really take it across the finish line." And modern Darwinists tend to say that, "Oh, well, that was just an error of thinking on Darwin's part," but it's actually a very profound question about evolution and adaptation. Just what is the nature of adaptation? How is adaptation inherited from one generation to the next? You couldn't really get evolution really without having some mechanism of heritable adaptation, and and there was no way of explaining heritable adaptation adequately, and that's why pangenesis died, and it's ultimately why Darwinism, classical Darwinism, sort of fell into a little bit of disrepute. And of course, this period is what Peter Bowler has described as the eclipse of Darwinism. All kinds of other ways of thinking about evolution started to come to the fore. Among them, of course, was the emergence of the concept of the gene. This happened, with the rediscovery of Mendel's work by De Vries and others at the beginning of the 20th century. The culmination of that way of thinking, of course, was Thomas Hunt Morgan's theory of mutationism. And Morgan was actually a staunch opponent of both Lamarckian thinking and Darwinian thinking. He thought both of them were utter nonsense, and this was kind of I think the low point in the eclipse of Darwinism. Morgan was just an amazing scientist. You just think about the kinds of things he did with genetics, some of the techniques that he brought to bear, tying specific mutations to specific locations on chromosomes. The idea of mapping genes on chromosomes was an absolutely brilliant idea. He won the Nobel Prize for it, for heaven's sake. And and this planted very firmly in people's minds that the secret to heredity was solved by the discovery of the gene. And of course, this posed a great conundrum for people who were still trying to keep the Darwinian flame alive. Among them, Ronald Fisher, for example, Sewell Wright, JBS Haldane. And they also pulled off a brilliant trick. Namely, they took principles of population genetics that had been established basically as also an anti-Darwinian argument, and actually reconciled Mendelian genetics with the Darwinian way of thinking. And of course, this was the genetical theory of natural selection that Ronald Fisher wrote, as well as being elaborated on by Sewell Wright and JBS Haldane. It was an absolutely amazing transformation. I think easily on a par with the quantum revolution in physics and the theory of relativity, in terms of the kinds of contradictions that are reconciled, and the way it reconciled it was absolutely brilliant. And this set basically in stone the notion that, well, if we're going to have Darwinism, then the way to go is by focusing on the gene. And of course, Evelyn Fox Keller has described this as the century of the gene. It was such a dominant concept and such a well-established concept that basically that was the only place where scientific progress could be made. And that was the origin of the modern synthesis, and it basically remains at the heart of the extended evolutionary synthesis that we spoke about with Massimo Pigliucci as well. But the gene is focus there.
Yeah, yeah, and I think one of the points that came up in the discussion was Massimo was saying, well, we've known that more is selected than the gene, and we've moved away from that perspective. And when you were explaining, why the gene-centric view doesn't work, he said, well, we don't have to, accept that. But then later on in the conversation, when it came down to this topic coming up again, he did go back to the gene-centric view, and then you pointed out, well, it's still gene-centric. So this goes back to something I mentioned before we started the live stream. I wanted to ask you that whether it's the extended evolutionary synthesis or it's whatever, evo-devo, whatever we're going to call it, it's still going to fundamentally be based on a reductive gene-centric perspective, which is what limits it in terms of its explanatory power.
Yes, absolutely. And the sentiment is good. Certainly there's lots of other dimensions to evolution than simply gene selectionism. Even Richard Dawkins admits that right now. The original title of his of the extended subtitle of the extended phenotype was the gene as the unit of natural selection. And, he regarded, going off into organisms and behavior as kind of a departure from that kind of pure gene selectionism. But the reflex still is to go back to gene selectionism, no matter what. And this is one of my criticisms of the extended evolutionary synthesis, which is that it's kind of a grab bag into which you throw all kinds of different things. But when you start to explore some of the implications of that, it's always back to the genes. And therefore, one of my criticisms is there's really not much new in the extended evolutionary synthesis. And in fact, they're making the same mistake that the modern synthesis has, which is that it doesn't recognize the essential nature of what life is, namely that it's functional, that it's purposeful, and that it's intentional, and it's intelligent in many ways. And without that, I don't think you can build a coherent theory of evolution, never mind a coherent theory of life. And if you don't consider this in your evolutionary thinking, then you're going to have a problem. Now, the contradiction for me that I mulled over for a lot of time before I finally just made the jump, for some of the original titles that I was tossing about, for things like purpose and desire, for example, was biology's second law. And I still thought, you can be a good Darwinian, that natural selection was biology's first law, but that you have to somehow bring in biology's second law, which is this concept of homeostasis. That word has come up a few times in our conversations, and the more I thought about homeostasis, the more it became clear to me that homeostasis really is the basis of the intentional nature of life. And when you admit intentionality and purposefulness to the concept, which you have to do if you're going to have a full understanding of what homeostasis is, that runs smack dab into Darwinism, and the whole point of which is to try to explain evolution without referring to those properties. And I finally just decided I couldn't support the Darwinian idea anymore. So I dropped the idea of homeostasis as biology's second law, and came to the conclusion that no, actually, homeostasis is biology's first law, and all of our thinking about life and evolution has to start there. It's a fundamental property of life, and without that, you're only going to be able to explain a fairly limited range of phenomena about life, including evolution.
Yeah, that's a good way of putting it. And I guess to put it in other words, if the diagnosis of the phenomena itself is given an erroneous label from the start, then you will be limited in terms of what tools you're going to use to try and explain it. So
Yes.
if purpose is not accepted, if the idea of as Noble puts it, we've got causation the wrong way around, right? If we accept that, physiology has nothing to do with evolution. If we accept the gene-centric perspective, then you'll just have it. It's almost like going back to Kuhn's idea of incompatible paradigm, just two different ways of looking at the same phenomena. And
Yes.
if you accept, actually, you can have a purpose paradigm biology. It's epistemically fruitful. And one of the papers that Noble recently wrote, it was actually on the benefits to science by assuming purpose, as opposed to assuming a gene reductive perspective. And the example that Noble keeps bringing up is the Human Genome Project, and the billions have been spent, just trying to map out, and try and find correlations between diseases and certain strands of, DNA. And one of the examples he gives is it's almost like a ship going in the wrong direction with all these people on it, and it's going to take a long time for science to do a U-turn, because it's very hard, to think we've spent billions going in the wrong direction.
Yeah, and certainly, it's useful to know the human genome, and it's useful to be able to correlate particular sequences of DNA to to particular expressions. This is the kind of issue that I think the gene-centric view largely unexplores, which is it largely leaves unexplored, which is how do you get from sequence code into function? And of course, Jim Shapiro, among others, has been in understanding the dynamics of the genome. And of course, Barbara McClintock was there right at the beginning with her conception of the genome as an organ of the cell, right? And she was thinking about it in exactly the right way. And there have been some interesting insights that have come from the Human Genome Project. I think we have a better understanding of what had pejoratively been called junk DNA. That it's really kind of a very important part of the dynamic nature of the transition from sequence code to function. There's a vast territory there to explore, and the Human Genome Project has certainly opened up some territory there. So I give it credit, but when you're talking about diseases and form and adequacy of function and those kinds of things, it's the adequacy of function that's the important part. If you're talking about a disease, you have to understand something about how the function has been biased in a particular way that leads to disease. And when you're talking about evolution, for example, you're talking about expression of something, and certainly genetic hereditary memory does play a role in that. I've taken kind of a leaf from what Ernst Mayr has said, which is that evolution is adaptation informed by memory, and a very powerful way of thinking about it. But where the gene-centric idea goes wrong, I think, is that it's first of all, right at the very beginning of the expression of function, it doesn't really, gene selectionism doesn't really account for all these intermediate steps, and the the real important thing is the function itself. And of course, this is one of the reasons why I'm bothered by this distinction between genotype and phenotype. Their expression of genes is a function. It's a phenotype. So where do you draw the line? You end up drawing a line at some kind of trivial boundary that says, well, the genotype is your sequence code in the genes, all right? But the sequence code is not memory; it's tokens of memory. What matters is actual memory, which is a dynamic function. And of course, then we come back, of course, to Barbara McClintock's notion of the genome as an organ of the cell, and it participates as much in the phenotypic expression, as you will, as does any other function in the cell.
Yeah.
And so there's no distinction there really to be drawn. And the only reason it's there really is to prop up this idea of gene selectionism as the primary driver of evolution. And, it's like if it didn't exist, we had to invent it. And the genotype is the invention of that need to be able to maintain the gene-centric view of evolution.
Yeah. And it's really interesting that you put it back to McClintock's idea of the genome being an organ of the cell, because I was thinking back to the selfish gene's exact words are that the genome is sealed from the outside world, right? And just within about a year's time, roughly, it's going to be 50 years since the publication of the selfish gene, and it's still the popular idea. It's still taught in universities. It's still the predominant idea. And when I look back to, say, some of the things that have been published and even put out by prestigious institutes and universities, ideas which completely contradict the genome being isolated, or in fact the way that your own book was published 24 years ago by Harvard University. So we're not talking about the fringes of science. We have these publications coming out of the third way guys. We're seeing this stuff coming out right at the cutting edge, but still it's not affecting the mainstream dominant narrative. It's very hard to understand why it hasn't trickled in, why it's almost like a platonic ghost. It's just continuing on with the same mantra. And even the discussion between Noble and Dawkins, 2 years later, Dawkins his book in just October this year, The Genetic Book of the Dead. And when I went through it, he promised to address the discussion that he had with Noble in that book. For the last 2 years he had radio silence, and he simply repeated the same thing he said, that genes are causal, that it's not the case that the organism is actually doing the causing. And all the evidence of the tubulins and the sensitive nature of the cell and how it modifies its mutation rate, its proofreading, its ability to express, and how new sequences are selected by the immune system to fight off viruses. All of that evidence that he gave in the debate 2 years ago was totally ignored, and he simply repeated the same mantra. I just find like the gap between what's been happening in molecular biology and what's being taught is just so wide, and I just don't understand why.
Yeah, I think this is tied into a topic. I think it came up in our conversation with Massimo, Stephen Jay Gould expressed this eloquently, as he often did, and he spoke about we have to have. He was talking about the relationships between science and religion, and he trotted out this argument of that we can all get along if we have two non-overlapping magisteria. And of course, what defines a magisterium is you have an internal set of principles that defines what's inside the magisterium and what's outside the magisterium. And of course, when you're talking about science versus religion, it's often portrayed as one is logic and the other one is revelation. All right, those kinds of things. But and the Darwinian idea, in particular, the gene selectionist idea, constitutes its own magisterium. And when you talk about gene selectionism, it's internally a very logical, very consistent way of thinking, and so you can understand why people who are inside that intellectual realm think that, well, anything outside of it is not really relevant, and it may not even be scientific, and therefore we don't have to pay attention to it. And this, I think, is one of the principal problems with modern Darwinism, is that it is enclosed in this intellectual bubble, that the gene is the vehicle for hereditary memory, and and it makes a lot of sense. Excuse me, until you start delving into just how is it that sequence code is translated into function. And of course, at the cellular level and molecular level, we're becoming very aware that there's this incredible dynamism. It's influenced by the physiology. One of the things about the interesting things about the increased understanding of epigenetic mechanisms is that it's very clear the way in which the experience of a cell or an organism or whatever can feed back onto what the or what parts of the gene sequence code is actually expressed, with these methylation markers and those kinds of things. And when you start delving into that, then you start seeing things like the fallacy of the Weismann barrier, and this is the thing that has been propped up for a long time about, to defend the Darwinian idea. Okay, you can, and Ernst Mayr fell into this trap as well. You can say, okay, well, adaptation happens. There's all these dynamic things that are going on. Different parts grow, and different parts, disused parts are shrink and fade into unimportance. But in the end, none of that really matters to evolution, because you have this germ line which is held pristine, and whatever happens in the experience of the organism doesn't really matter to evolution. It does matter to fitness and these kinds of things, but none of that stuff is transmitted into future generations. And we're discovering more and more that no, that's absolutely wrong. And it is they are transmitted into future generations. And the Weismann barrier was a particular source of trouble for me. And so, I I looked into the history of this. I I had a choice when I was an undergraduate student. Do I become a scientist or do I become a historian? Because I just really loved both subjects. And so I've always had this kind of avocational interest in history. So I delved into the history. And Weissmann proposed this because there was a philosophical need for a pristine germline, and it was needed because he wanted to prop up this notion that heredity lived on the chromosomes somehow, and if you delve into the history of it, Weismann had all kinds of strange ideas about it. There's various kinds of myths that have built up around it. The whole issue of cutting the tails off mice and seeing if you end up with a race of short-tailed mice. The actual history of that experiment is not the legend. It's not even certain that Weismann even did the experiment, to be honest. And then when you look into how do you explain this for all evolution, it cannot be a general theory of evolution because only a limited set of organisms actually have a sequestered germline. When you talk about plants, for example, or you talk about other kinds of heredity or other kinds of ecosystems, there's no concept of a germline there. And so, if you're going to have this theory of segregation of the germline as the fundamental prop for genetic theory of natural selection, how do you explain the evolution in everything that doesn't have a germline?
Mm.
And so there's all kinds of interesting contradictions in there, but people still cling to this notion that you have to have a segregated germline, and because philosophically you need to have a segregated germline to be able to prop up your worldview, and this is one of the problems with this non-overlapping magisterium idea, and of course science and religion is one of the big ones, but there's magisteria everywhere, basically little territories that people coalesce around and defend,
Yeah.
and are resistant to ideas coming in from outside. And the big issue with the third way is that the people who are in the Darwinian sphere don't really think about the wealth of evidence out there that's contradictory to it, because it's not within the internally consistent and coherent intellectual realm that people have built.
Yeah, absolutely. And the way I like to think about the discussion between neo-Darwinism and the third way is like the discussion between Descartes and Spinoza. So
Mhm.
back in the 17th century, Descartes famously said that if you knew everything about the sperm, you could predict the future behavior and form of the organism. So
Mhm.
that type of reductive thinking, it's like a very crude central dogma, right?
Yes.
Um, and it's so neat. I mean, if I was to play devil's advocate, Professor Scott, I would say, but it's so neat and pretty. It's such a simple,
Mhm.
reductive idea. Why would you third guys come and, bring integrative and holism and
Yeah.
all this
Mhm.
these ontologies, which are way more complex and require a lot
Mhm.
more brain power than this very simplistic idea?
Yeah. This prompts another one of my little rants. That this notion that that it's so internally consistent and neat, and therefore it must be right. That's kind of one use of one way in which the concept of Occam's razor is applied. And you see this application everywhere. If you look at reconstruction of phenologies, for example, from DNA sequence and phylogenetic trees and things like this, at the center of it is this idea. Well, which is the most probable one, and therefore the most probable one is probably the right one, the right sequence, the right pattern. But if you think about the incredible novelty and adaptability that life brings to what it does, which is persist and reproduce, there's no reason why Occam's razor should even apply. That that biology should, at first step, reject Occam's razor. You expect complexity. You expect lots of different ways of solving a problem. The path from the past to the present is tangled. It's very complex, and you actually expect that from biology, and therefore, you know, propping up your worldview using some variant on the Occam's razor argument, it doesn't really hold a lot of water, I think.
Mm, absolutely. And we also know this from physics. A very neat idea of an indivisible atom is way more
Mhm.
simple than the quantum world with relational, informational, many worlds, Copenhagen, interpretations. But it's not right. Something else I was thinking of is the implications from the third wave perspective and the neo-Darwinian perspective. The neo-Darwinian perspective, the ultimate rationale of life is the preservation of our genes. And the third way's implication would be, well, the ultimate rationale of life is to adapt to its environment, to evolve. So it's a lot more of a colorful way of looking at biological discourse. I wanted to bring in something which you mention on page 297, and this is to do with the internal physiology and the external physiology. And you have a really brilliant way of explaining this in one of your videos where you go over the bucket example in the cell and how we define what is the boundary. So firstly, it's we know it's very clear and quite intuitive, the internal physiology, right? So the organism stops at, we define it at its skin, right? We define, okay, this is what an organism is. But why is that not enough to limit physiology? Why is it that we have to have this extended idea?
Yeah, this is central to the notion of what an organism is and really what life is, and I make the point that organisms really are devices for dividing the world into two environments. You have an internal environment and you have an external environment, and we imagine that life is what goes on in the internal environment, and there's all kinds of wonderful details and things in there to work out. This is the focus of what we as biologists do. But if you think about even something as simple as a cell, for example, it's an incredibly complex, highly ordered environment that's created inside the cell membrane. And thermodynamically, that shouldn't be, that you should, that these kinds of very highly ordered environments should degrade very rapidly towards disorder, but yet we have this persistent orderliness that goes on inside a cell, and it's not only persistent orderliness, but it's a persistent specified orderliness. And when you look at the requirements for that kind of thing, you have to do a couple of things. You have to build that specified order as rapidly as the second law of thermodynamics is forcing it towards basically maximum entropy. Excuse me. And in order to pull that trick off, you have to manage a flow of matter, and you also have to do work on that flow of matter to take kind of disordered matter that's outside the environment and impose order on it as it flows through the cell. So when you're talking about living things, you can't really talk about them as objects. We talk about a cell as a noun, but a cell is actually a verb. It's a process. This continual flow of matter and energy in through the cell actually persists, enables a cell to persist in its orderly form. If you don't have that balance, then the cell dies. And so central to this concept is this notion of what I call an adaptive boundary, which is the cell membrane. The cell membrane is what manages it. And when you look at the implications of that for internal and external environments, and the example I use quite frequently is how you maintain a particular salt concentration inside a cell. Right? You have to be able to transport, say, sodium ions in. And simple conservation of mass says that for every sodium ion you transport in, you're depleting it from the external environment. And so whatever physiology is going on inside the cell that results in a persistent concentration of sodium membranes is also imposing physiology outside the adaptive boundary. And of course, this comes from simple principles of conservation of mass. So when you're talking about physiology, you cannot limit yourself to what's going on inside the cell. You have to be able to think about physiology in terms of the imposition of physiology on the external environment as well. And this is central to the notion of the extended organism. So the cell has a physiology going on inside, but the implications of what that entails means that the physiology inside is also imposing a kind of physiology outside as well. And so that's the notion of the extended organism. And when you're talking about, excuse me, when you're talking about being able to maintain a specified orderliness over time, you're really talking about homeostasis there, right? And it's a short leap to say that, well, there's also extended homeostasis, whatever mechanisms are imposing persistent orderliness inside the cell, it's doing the same thing outside the cell as well. So you not only have extended physiology, but you also have kind of extended homeostasis as well. And this was one of the reasons why um, it's a bit of a provocative hypothesis, but why I say that the termite mound is as alive as the organisms that are constructing it. Because, when you're talking about these adaptive boundaries, the cell membrane is, perhaps the smallest one. But these things can nest; they can cooperate in associations. One of the fundamental associations you get inside bodies are cells organized into sheets that are called epithelia. And if you look at the structure of any kind of internal organ body, you find that they're actually kind of nested sheets of epithelia, and then you just build from there. You have epithelia that coalesce into organs, organ systems, and so forth. We tend to draw the ultimate adaptive boundary, as we've said, at the skin, but then why limit it there? What about living things that don't have skins, like superorganisms, colonies of social insects, ecosystems, microbial mats, all those kinds of things. And so life, ecology, whatever, the entire biosphere consists of these various associations of adaptive boundaries. And if you take the logic that what goes on inside an adaptive boundary is imposing some kind of, physiology, life to outside the boundary, then it's a short leap to say that, well, actually the Earth is the biosphere is as alive as anything in it. So
Yeah.
so that's the logic.
Yeah, absolutely. And my last sort of question to you is how this relates to the wider discussion in science between substance ontology and process ontology. And while you were speaking, I remembered a really nice quote of John Dupree, because he's really focused on this idea of the ontology of science. So normally, from a things perspective, things have boundaries; they do not flow into each other. And one of the things that I found really interesting about Dupree's work, who's also part of the third way of evolution, is, from a substance ontological perspective, things really exist. However, from a process view, and this is his direct quote, enduring things are never more than patterns of stability in a sea of process. I absolutely love that quote. I have it written down because it's John's really got his way with words, and that's the way I see. I mean, the way you're describing your findings in the extended organism is dovetailing nicely with this shift, this ontological shift that we need to have in science about process. I guess the question I want to put to you is something which John highlights, is one of the difficulties with the process perspective is that a process is hard to identify and characterize in a thing in a substance ontology. Looking from a substance ontological perspective, things do not flow into each other and have distinct boundaries. So do you think one of the resistances to the third way of evolution, and in particular what you're saying right now, is because things are no longer neat and it requires a lot of difficulty in trying to understand what's going on from a process perspective than it is from a substance perspective.
Yeah, it's an interesting question. Certainly, the tradition of 20th century science in the well entire 20th century, actually extending into the 19th century, is that um, the key to being able to understand life is to delve into the uttermost molecular details of what life is. And this is a very object oriented um, concept, right? And the gene, defined as a sequence code of DNA, for example, is very much of an object oriented way of looking at heredity. And this is one reason why, for example, Fisher's statistical genetical theory of natural selection, it took as its inspiration gas statistical mechanics of gases, and it was a brilliant synthesis. I take nothing away from it, but it was still focused on basically object genes. You have an object gene, you just define it as doing something to the function of the organism without really delving too deeply into what the function is. But life is not objects. Our entire language of science is really centered around things. A tree is a noun. I'm a noun, for example. My dog is a noun. These kinds of things. It's we perceive it as an object that's just is. It exists just like any object does, just like atoms do, and so forth. But thermodynamically, that doesn't square well with what life is, which is this process-oriented thing. And coming back to the ways that we build intellectual bubbles around ourselves, for example, is what I think is the trivialization and misunderstanding of the concept of homeostasis. That homeostasis is the outcome of the operation of a machine, right? And you touched on this a little earlier. Dennis Noble has said that we get cause and effect entirely backwards, and this is really true for Claude Bernard's understanding of homeostasis. He said that the free and independent life is the condition for a life, right? And so the clear implication there, and if you delve into some of his writings, it's clear that he thought this, was that mechanism streams from homeostasis, from this fundamental property of life. In the early 20th century, for example, Norbert Wiener, another brilliant mind, is responsible for this largely. You've turned the concepts around. You're saying that homeostasis is the outcome of a mechanism, when in fact, the origins of the concept were exactly backwards. And this is the fundamental problem that I think that we are dealing with right now, in terms of the definition of life, what homeostasis is, and the implications of it for evolution, is that we need to get cause and effect right. And one of the I think relatively common themes in the third way is that we've got cause and effect exactly backwards, that we need to actually focus on what is fundamental about life, and from that everything streams, not the other way around.
Yeah, absolutely. And that's certainly nothing short of a gestalt shift in terms of the way that
Yes.
future biologists are going to be looking at organisms, and not only in terms of the actual how do we define one, but in terms of causation is something absolutely central, and it's been sort of the whole discussion has just been dominated by this one-way causation in a way that it's almost like a given. And the onus is no longer on the neo-Darwinists to provide evidence for it. It's almost like we have to provide evidence against it, which we have, but it's still dominating. So just before we end, what I wanted to do was share my screen in terms of the Udemy course, which I signed up to, and I highly recommend it. Does. So just a little bit about this. I mean, I've signed up to many courses during my time, but this one in particular I really enjoyed because you go back to the history of the ideas, and Bernard is mentioned, homeostasis is mentioned. You also go back to many of these things from a very elementary perspective. So I highly recommend, if you're watching this live stream, to sign up. I'm going to leave the description in the comment below. And I'd love to have you back at some time in the future to discuss another topic.
I would enjoy that very much, Sabur, and thank you so much for promoting that course. I developed it primarily to get this word out to people who may not be steeped in biology and evolution, because I think the conversion of worldview, the Gestalt view, as you put it, is going to come from lots of perspectives besides the strictly scientific one that we talk about. It really is a broad philosophical and societal level discussion. And thank you for promoting it. And I hope people take part in it and enjoy it. There is a short course that I put together that's free. There's a little bit of a nominal cost. I try to keep the cost of the Udemy course relatively low. But if you like a taste of it, then I do have this 8-episode series on YouTube that delves into some of these issues, and I think that you've put the link to that in there as well. But please do take the course, because it's very detailed. We get into all kinds of fascinating topics there, and it's actually pitched to lots of people besides just us biologists.
Yeah, absolutely. So thank you so much, Professor Scott, for your time, and I hope to see you soon.
Thank you. Thank you very much, Sabur.